Hacker Warehouse, a USB sniffer, and a t-shirt, hit it. And some of these things I can't throw at all. Thank you to our lovely sponsors. Up next we have James Forshaw, researcher for Google Project Zero, winner of Pawn to Own sub-contest, and speaking today on Windows sandboxes.
Good afternoon, ShmooCon. It's good to be here. Good to see so many people actually turn up to my presentation. As said, I am a researcher for Google's Project Zero team, but that's largely irrelevant here. I tend to specialize in sort of Windows type stuff. So Windows exploitation, Windows vulnerability research, mainly around local privilege escalation, so sandbox escapes or local system privilege escalation. And I'm very much focused on logical vulnerabilities. I don't tend to use fuzzers unless I really have to, so I've never met a logical vulnerability I didn't like, which is always good. So I'm obviously going to be talking about sandboxes, not kitty litter, but it was sort of the cutest sort of sandbox-like related image I could find, which also had a free license. So I'm going to be speaking specifically about user mode sandboxes, sandboxes which are implemented for applications without sort of requiring substantial privileges. So you don't need a kernel driver to modify the operation of the operating system itself. And it's obviously focused on Windows. There will be the odd sort of counterpoint of this might be something which, say, Linux could do or OS X could do, which Windows can't, or vice versa. But it is about Windows application sandboxes. So to just sort of run into this, while I'm obviously not going to write a sandbox on stage, that'd probably take a bit too long, I want to at least sort of go through some of the basic ideas of why you'd want a sandbox or what sort of ideals you'd want in a sandbox. And then a bit about the sort of the security architecture of Windows, which allows you to do it from a user mode perspective. Because if you were to require kernel mode access, it becomes a lot more difficult because actually modifying the operating system at that level isn't necessarily as well supported. So the first thing, kind of almost the fundamental aspect of a sandbox, is that it's something which is easy to get into. We don't need to do anything sort of clever or substantially modify the operating system. But any attack code which might end up in the sandboxed process, whether it be, say, a web browser, and you get exploited using a remote code execution vulnerability, you really want it very difficult for them to get back out again and then affect the rest of the operating system. That seems fairly obvious. We'd also like to protect users' data if we can. Most of the sort of important part of your computer is not the bits and bytes which make up the actual operating system itself. It's the data you've written, the documents, the passwords you save, the financial information, which could be interesting to an attacker. So in an ideal world, we'd like to stop them being able to disclose your information as well. But we've got to work within the limits of the operating system. If the operating system provides us with no ability to do what we want, well, we're kind of stuck. We have to make do and hope that it is sufficient for our needs. And finally, and this, while obviously not being able to break out the sandbox is pretty key to a useful sandbox, if it ran at 100 instructions a second, that wouldn't be much use to your average user. It might be if you had a very specialized application that you'd be willing to take that substantial performance hit. But for an average user, if their web browser takes an extra half a second to load, they may actually notice and get pissed off about it. So it sort of ends up that if you look at most of the sort of common implementations of sandboxes out there, so things like Chrome or IE's Enhanced Protected Mode or Adobe Reader, they tend to operate in this sort of model. I'm not saying this is necessarily the only way you could do this sandbox, but it's usually fairly typical. So what you do is you have two levels of privilege as the normal user. You have your sort of user level privilege, which is when you log in, that's what you get. And you can run your applications there. And then you construct some sort of lower privilege ICE container in which you can run your sandbox process. Now, of course, a process which, the sandbox process, if it can't do anything useful, if it couldn't access that web page you were trying to render, it's kind of useless. Again, there may be certain classes of code which having something which can't access any external resources would be beneficial, it's generally fairly limited. So normally you would have then a mechanism to get out of the sandbox process, talk to a broker, in this case, as the normal user, and on its behalf, access resources. So that's the sort of principles of the types of sandbox, or the way in which you may want a sandbox to perform. So how can we actually implement this in Windows itself? Now, Windows has actually got quite a rich sort of security architecture, and obviously anyone who's used Windows knows it's completely secure and has never had any vulnerabilities or problems. But actually, under the hood, it actually is pretty good in terms of the level of flexibility it gives you. And the core to all this, the thing which effectively secures most of the resources in Windows, is the security descriptor. And this is basically a binary blob of data which describes the access requirements for that resource, whether it be a file, a registry key, a process, etc. Now, security descriptor, at least post-Vista time, has sort of three main important parts to it. The first one is the owner, and the owner represents who actually owns that secured resource. Usually it's the person who created it, although not necessarily always. Secondly is something called a mandatory integrity label, which I'll go into a bit more detail. But basically this is sort of a mandatory access control mechanism to provide sort of a very simple way of reasoning about whether you can access that resource. And finally, the sort of meat of the security descriptor is the discretionary access control list. This is the thing which defines who can access that resource and what privileges it will give you. So, for example, there may be an entry which says administrators can write to this resource, but normal users can only read from this resource. And we're going to repurpose this in a sandbox to actually implement our security features. So what actually defines who you are? It seems like it should be a relatively obvious question to answer, but of course, in Windows, it isn't necessarily that obvious. Every process on the system runs runs with a specific access token, and this token is used to identify the security context in which that process is running. So, for example, it contains information such as your user. Now, when you see your user, it's like, say, I'm called James, whatever, that's your username, but that obviously is mapped into an actual sort of unique identifier behind the scenes, so security identifier, or SID. And that's used everywhere. The security identifier is used as the unique metric for identifying all securable entities, basically. The second thing the token contains are groups. And you can sort of think, if you know anything about sort of, say, Unix permission structure, it's basically the same thing. You have a user ID, and you have a list of groups which you are also assigned. And resources potentially can be accessed based on just your user itself, or whether you're part of a group which has access to that resource. You then have the counterpart to the label, which was in the security descriptor, the mandatory label, which is just defined as a level. So in this case, it's medium. That's sort of the default, sits in the middle somewhere. And obviously there's low, high, untrusted, if you really don't trust the person. And finally, some privileges. These are sort of additional capabilities the user has, and I'm not going to go into them much because generally a normal user doesn't have anything which causes serious damage. If you're running as an administrator, for example, there's a privilege to bypass security checking on processes and those sort of things. So it doesn't really matter too much for normal users, so I don't need to go into it. So when we actually want to access a resource, we say to the kernel, can I open this file, please? Here's the name of this file, and go and open it. And when that happens, the kernel must actually make a reasoning against your current token and also the access control of the security descriptor, which is determining what access you can get. And those three components which I noted in the security descriptor are there with individual checks. So you've got the integrity level check, the owner check, and the DACL check, the discretionary access control check. Only if the access you require, so read or write, is matched by all three of these checks, will you be then granted access to that resource. If, for whatever reason, you ask for access which you do not have, it will just deny access regardless. It won't give you what privilege you could just about get. It will generally just say, nope, sorry guys, you can't have anything. Now, the IL check is pretty simple in essence. The integrity level is just a number from 0 generally to sort of 16,000. And it first does, is the integrity level in my token greater or equal to the one in the resource? If it is, that means from a mandatory control point of view, it's allowed access and it doesn't then perform any further operations. If it's lower, then it needs to do a very simple policy check. And each security descriptor has this policy which says what you can do if you meet the IL requirements. So it may say you can read and execute, but you can't write. And at this point, if you've got a lower IL, if you access, say, this resource with write access and the policy doesn't allow you, it will also then deny access to you. Otherwise, it just lets it go on, because ultimately, it's got to continue on and do the rest of the processing. The owner check is similarly simple. If you're the owner of that resource, we're given additional rights. We can modify the access control list itself, and this is there for a good reason. If you couldn't do this, you could end up locking yourself out of your own files, which would be kind of annoying. So you can always get back into your files as long as you own it. And then finally, the access control check itself is a fairly simple process again. What it does is I'm going to go through the list of what's in the security descriptor, the access control list, match it up to your token, and whatever the resulting access rights you get is what you get. So if you ask for read-write, in this case, we can find that we're granted it because even though one group only had read, it bypassed that and went to gave us read-write access. We can also do deny rules, so say if you're part of the users group, you're not allowed to have read-write access, and so again you get access denied. But because it short-circuits the checks, if you just say read only, that was sufficient to bypass the check, and the deny rule doesn't run. So that's the sort of basics of how the sort of security architecture in Windows works. It's generally slightly more complicated than that, but that's probably enough for getting along with. So we can actually go and do the quickest and dirtiest sandbox possible. And unsurprisingly, this was the quickest and dirtiest way of sandboxing Internet Explorer when Vista came out. So it has got precedent. And you just modify the integrity level. If you lower the integrity level of your token, then any resource, because all resources default to medium integrity if they don't have any explicit label, will deny write access. So you can read anything you like on the disk, pretty much, obviously subject to any other access control, but you can't write anywhere, or you can only write to very specific areas. And this is a sort of fairly simple way of doing things, but it doesn't really meet our ideal sandbox rules. Being able to read all your files has questionable value. Yes, you can't maybe persist, but I don't think it really helps much. And as is a common refrain from, if you submit any bug in this sort of area to Microsoft, you'll generally get back a, sorry, this is not a supported security boundary. And integrity levels in this case are generally considered as such. They don't consider Internet Explorer's protected mode a security feature. It's just sort of a defense in depth, I suppose, which is a problem when you're trying to write a secure sandbox. If you find bugs in the code, bugs in Windows, which causes your sandbox to fall over, there's a chance that they won't fix them as pressing security issues, or they may be unfixable. So we can do a little bit of sort of limiting of the damage you can do from this quick and dirty sandbox. You can also apply something called a job object restriction. And this basically is a set of quota restrictions you can apply to your process. So for example, you can say, this job can only ever have one process in it. And so if you try and create a new process, then it will fail, which is pretty good. But again, it's not a security boundary, because there's various ways out of this. You might be able to instantiate a process through out-of-process COM, for example, or you can use WMI to break out the job object. So it's still not actually a security boundary. It's just kind of a useful feature to have. So we need to get something a bit more restrictive, strangely enough. It needs to be something which we can do from non-administrative privileges. So we're actually quite limited. In an ideal world, we'd craft, say, a custom user. And this custom user will be what we run our sandbox under, completely unrelated to the current user running the main part of the process, the main part of the application. But unfortunately, we can't do that, at least from non-administrator accounts, and for good reason. If you could synthesize your own tokens with any groups you like, well, that's a quick privilege escalation issue. So we instead can use a supported feature, something which was added in Windows 2000, called the restricted token. And this allows us to do a few different things. We can disable groups in your token. We can delete privileges, but as I say, it doesn't really matter too much. But importantly, we can add additional SIDs, additional security identifiers to your token, which are then used as additional to the access check. So this modifies the way in which the normal access check, and there's an extra couple of diamonds on there. And basically what happens now is instead of just doing a check against the single owner or the single access control list, it does actually two checks. First, it checks your normal groups, for example, and then it checks your restricted SID groups, and only gives you access if both those checks succeed. And we can actually, by putting in security identifiers which don't exist, you can pretty much deny any access to any resource on the system. So that gives you both the restriction on reading arbitrary files, and also pretty much makes it impossible to write anything either. So yeah, we can do that. We can't obviously change the user's identity itself, and we can't sort of do certain things like removing linked tokens in user account control, but they're not security boundaries anyway, so it doesn't matter. Okay, so we now need our process. We've got everything pretty much ready. We've got our token, which we've synthesized and is super secure, and nobody could ever access anything using this token. So we call create process as user. This is a built-in function of Windows which allows you to create a new process running with a different access token. So we do that, and the first thing which you'll see is a crash. If you've got like a just-in-time debugger handy, or catch it, or Windows error reporting will come up, and the thing will just blow up. It's like, oh, okay. All this hard work, and you can't even run the process. And there's a good reason for this. Basically, your access token is so limited that when the process tries to initialize itself, tries to map in its DLLs, access sort of expected resources, it can't. It has no access in order to do that. And so it blows up before the process has even officially started. If you actually attach a debugger to that process, if you start it suspended, attach a debugger, it will blow up before the debugger even gets control. And that obviously makes it quite a tricky thing to debug. There's a few tricks around it. You can set manual breakpoints on the initialization function, and then it will catch it, but on the whole, it's an absolute nightmare. But let's say you get around that. So you can get around it. You can do tricks with Fred tokens and all this sort of crazy stuff, but we get past it. So we've now got a process which runs with virtually no permissions. That's great. So we have our sandbox process, we have, say, a broker process, but we've got the entire Windows operating system to attack. And maybe not every part of the Windows operating system is quite as secure as some of the other parts. Generally, files are pretty good. Obviously, the file system is pretty much the primary mechanism of attack, and that's usually pretty hot on making sure that the access controls are met. But certain other things, not always the case. So the first thing you could sort of think of is the actual attack surface of the kernel itself. The kernel is sitting there. There's a mechanism to do system calls into the kernel. And if you look at sort of a modern version of the Linux kernel, there's around 300, 310 system calls. So if you look on Windows, there's about 400. That doesn't actually sound too bad. Okay, another 100 system calls or so, it's probably all right. That's until you actually bring the user interface into it. And the user interface actually runs, for the most part, in the kernel. So it's also a kernel attack surface. And that has only about 1,000 system calls, give or take. And if you know anything about Windows exploitation, Windows local privilege escalation, one or two bugs have been found in this component in recent times. Yeah. So other platforms have it, I suppose, relatively easy. Linux has seccomp, which allows you to define sort of a filter on what system calls are allowed to be executed, what parameters you can pass to them. OS X has something similar. It has its sandboxing APIs, which you can do kind of a similar thing. But there kind of isn't as such something for Windows. There is something later on, which I'll point out. But in the general case, the only way to realistically hook system calls and prevent malicious code from abusing them would be to sit in the kernel. And then, obviously, if you're running an x64 version of Windows, the kernel is protected by PatchGuard. You can't actually technically patch the system calls anymore. So actually implementing your own system call filter without support from Microsoft is going to be a pretty tricky thing to do. Now, of course, not everything is exposed through system calls. In an ideal world, you'd have the minimum number of system calls you could possibly get away with, and then sort of augment it further along the line with other mechanisms to access kernel resources. So obviously, device drivers are just one of these types of things. Device drivers, obviously, on Windows support many different concepts. They're used for USB drivers. They're used for file systems. They're used for just general, I want something running in the kernel, which I can then probably blow up and cause kernel exploit. But device drivers expose themselves through device nodes, and these device nodes are things you can access. I think, obviously, again, in the Unix style, anything under /dev, this is basically the equivalent for Windows. But you can't just see it. It's actually sort of hidden under the surface. You can't easily see it, but there's tools such as WinObj from sysinternals, which you can actually view this sort of mysterious internal world of Windows. Now, you actually access these through the file system API. So you say to the file system API, the system call, open this device driver for me, and it has just a path name, so /device/something. And if I pass it this, say /device/harddisk/subname, whatever, doesn't really matter, this gets fed into the kernel's I/O manager. And this is the thing which actually handles the operation accessing this device. And that then splits this path up. The actual device node is /device/harddisk1, and that's what is exported by the device driver. But we've got this extra data, so extra part of the path. What do we do with this? Well, this is how Windows supports file systems. Effectively, what happens is you talk to the volume driver, say hard disk 1, and then you pass it the relative path from that volume. So what you see as the C drive is really, out under the hood, just referencing off one of these device nodes. So it splits it up into these two things, and it then looks up the actual driver itself, finds its procedure for handling create file calls, and passes the rest of that device path to the create file call. And this is referred to in Microsoft's documentation as the device namespace path. And it's basically a subpath into your device driver. And that's fine. That would seem to be perfectly acceptable. Devices have some security associated with them. So if you open the device, the kernel will do a security check. It will go against our access control list, which in our super sandbox means you can't get access to anything. But of course, it would be stupid of me to discuss this if there wasn't actually a problem with this mechanism. And that is, the problem is, by default, the device path is enforced by the kernel, but the security of the namespace is not enforced by the kernel. And again, this is for a very good reason. This is for file systems. File systems, if you access /Windows/notepad.exe, it knows that it's the file system's responsibility to do that access check. The kernel does not know how to extract the access control information from an NTFS file system. It's only the NTFS driver which knows how to do that. So it delegates the security to the kernel, unless you set a special flag. But what this effectively means is no matter how secure a sandbox you can make, how restrictive your token is, you can always get access to these device drivers which don't have security built in. And that's, you could consider a problem. So let's give an example of a device driver which does not enforce security at all for any token you can possibly come up with. Well, that's just not quite true, but we'll get onto that later. And that is sockets. So networking, Windows does not have system calls for connect, socket, bind, listen, all that sort of stuff. They're not part of the system call layer. They're actually implemented separately. But when we actually write code, and we want to run this in a sandbox, we want to see if we can access sockets, because it would actually be preferable if we can't make network connections from sandbox applications, because there's local services listening, there's potentially remote services you could attack, and while you might not be able to privilege escalate locally, you could possibly do lateral transfer through exploiting it that way. So we write a little test. We go to MSDN, look up the socket API, and copy and paste a nice example from that and put it into our code. And we test it locally without the sandbox, and it works perfectly. And so we took it in our sandbox, and we hope it fails. And it does fail. It fails here. It doesn't even initialize the library. Now that's awesome. What can possibly go wrong? Surely that proves, without a shadow of a doubt, that sockets are not accessible in a sandbox. But unfortunately, the device which actually implements the sockets is the ancillary function driver, one of the most misnamed, strange named all it does is sockets. Why it's called the ancillary function driver is beyond me. And we can interact with it. And crucially, not only do you interact with it through its namespace directly, even though actually it turns out it completely ignores whatever you pass after it, but it will open it anyway. It doesn't enforce any security whatsoever. It will quite happily open sockets for you from the most restrictive sandbox you can come up with. And then you do some further interactions using device I/O control, sort of like that. So that is how you do a connect call in a super secure sandbox, and you can just do a connect and then talk to anything you like. So unfortunately, there's actually, as far as I know, no way to stop this. Of course, if anyone actually knows how you can stop this on a general case, especially on Windows 7, then I'd be quite interested to hear it. You could add a firewall to the process, but you probably need admin permissions to add a firewall rule, and it's a bit abusive to just change someone's firewall rules for just do a bit of sandboxing. You can do something about this on Windows 8 Plus, but A, how many people are actually running Windows 8 Plus? And it requires a bit of stuff you probably don't really want to do anyway. Okay, so I'm just going to do a quick and just show some stuff. Hopefully it works. So I've written actually some tools to do enumeration of sandbox attack surface wherever possible. So one of the tools I've written is something which will actually check from a heavily restricted process what devices you can access. And specifically what will just allow you to open the device node itself. And I was hoping to get these released prior to ShmooCon, but unfortunately I didn't count on the requirements I needed to do to release code from Google. So hopefully in the next few weeks I'll get that out into the real world, put it up on GitHub, and you can use them yourself if you are so inclined. But in this case, what it allows you to do is you can choose, say, a heavily sandboxed process, such as one of the Chrome renderers, and take the access token from that renderer and use that to determine whether you have access to any of the secure aspects. So we can see it's PID 3256. 3256 slash, and hopefully, right. So that's more than zero. You would hope that you would not be able to access any device nodes at all, but we can, if I actually put in one more option. So some of these, the ones with the numbers, these are auto-generated names, so they don't have a specific name. You can usually work out what they are by doing a mapping. So for example, you can access a fixed button hanging off ACPI. No idea what that is, possibly the power button. Why it needs a driver, I'm not quite sure. You can access the parallel port for virtual DOS machines on this 32-bit machine. You can access the USB root hub. I'm sure there's possibly some fun which you could get up to with that. And some other ones, obviously AFD's in there. NTFS one is obviously interesting. I don't know whether you can actually do anything useful with it. I've had a quick look and it didn't look obvious, but this is all an extra attack surface. This is all stuff which could have failure modes which cause problems to occur. And there's not a lot you can do about it. So that's sort of our attack surface. So we've gone and said, well, there's going to be stuff which we can't secure, but okay, it's better than nothing. So we're going to now go for how you actually then get access to resources. As I said at the beginning, it would be a fairly useless application if you could not access any resources at all. If you could not get that HTML file, although obviously we've proven that you could if you wrote some native code to drive the socket driver, it would be pretty useless. So one of there's sort of two schools of thought of how you do this, and depending on the application will depend on what decision they've chosen. The first one is you actually just modify the resources you want that application to see, and modify them so that their security will allow you access, even with your silly token you've generated. The alternative is you actually just heavily restrict everything, and you provide the broker to mediate all access. And each of these have their own pros and cons. For example, accessing directly generally has a performance benefit, because you're not having to talk to a broker, which then has to open the file, and so on. But the broker itself gives you a way of mediating and controlling with finer grain what you can actually do. And that becomes important when you think of some of the hidden functions of the Windows operating system. So yeah, direct resource access, you just modify the permissions, and then the Sandbox process can just open them directly. And yeah, the trouble with direct access is if the resource you're accessing has unexpected operations on it, or undocumented operations, or even documented operations which have security impact, well, they can be done because you're accidentally accessing the resource. There's no way of filtering that out. So one of the ones I've used a number of times now is to abuse the fact that the Windows registry, which is used for sort of configuration settings, has an ability to create symbolic links. And if you know anything about sort of exploiting symbolic links, this is usually sort of not an ideal situation to be in, because you can potentially get higher privilege code to access your registry keys and redirect access to some arbitrary part of the registry, and from then get privilege escalation. So one of the bugs I actually found in IE's enhanced protected mode was there was a low privileged area of the registry you could write to as your Sandbox process, but then a system service, the audio service, was actually responsible for, was also reading and writing into the same area. So it was possible to obviously add your symbolic link from your low privilege process and then just wait around a little bit until someone calls the audio service, and all of a sudden it's going to start writing your arbitrary registry keys. And from that you can then do a Sandbox escape, and it's actually reasonably easy to do. I've actually put the link down at the bottom. It was one I found at Project Zero, so you can actually just look up the implementation of this. And yeah, so it's sharing that access is quite a tricky thing to do right. And by allowing you the ability to create these keys, because you need to have the ability to say, open this key for me, you can potentially affect a Sandbox escape. Now the real problem with this, obviously the audio server is a Microsoft part of the operating system. It's not written by a third party who doesn't have access to all the facts. It was written by Microsoft, whichever developer did it, and there was obviously a rationale behind it. And the reason it worked is because basically the documentation doesn't tell you that symbolic links exist, or at least it hints at it. It teases you a little bit and says, hey, there's symbolic link support in the registry, but I'm not going to tell you how it works, because why should you bother? So if you go and look at MSDN, look at the create key function, you'll see this reserved parameter, which not only is reserved, it obviously must be 0. Can't be anything else. Nope, has no other use. And one of the fixes, the fix basically for these types of bugs, is you can specify it is documented. It's not documented on this page. It's documented on one of the internal kernel ones. And even then, it doesn't actually tell you what it does. You kind of imply from the option name, it opens the link. Okay, it might open the symbolic link. The description, the key is a symbolic link, provides you no value whatsoever because, and all this does is it will, instead of opening the destination, it will open the link itself, the actual symbolic link. It's like the read link system call in Unix. But it's not documented. Why isn't it documented? Who knows? Microsoft obviously know about it because when they go and fix these bugs, they go and put in value 8 or whatever it is for the option. Thanks, Microsoft. Very generous of you. Okay, so we've now gone, we can't support direct access. This is never going to work. So let's go instead for completely all through the broker. Everything is going to go through the broker, all file requests, all registry requests, everything. Now, obviously, this has a reasonable performance impact, because if every read and write is going through the broker, it's going to hurt. But you can enforce policy. So let's look at file access. And files are pretty useful things to be able to access. So let's, for example, we'll hook the create file call. This is the Win32 function to open a file and pass them all to the broker. Okay, so what we want is a nice simple path which we can verify. Say you only want to write under a certain directory. It'd be lovely if there was a way of making sure that we could only write under one directory. Of course, Windows, or Win32 specifically, kind of muddies the water a bit about what is a real path and what is not a real path. So these are some of the paths you can pass to create file, which do obviously all two completely different things. So you can pass a relative path, that seems obvious, relative to your current directory. You can pass an absolute directory, passing in the drive letter absolute path. You can then do some odd-looking syntaxes. You can do //./ and this is called a device path, and it's canonicalized, which becomes important. Or you can do // which is also a device path, confusingly, but it's non-canonicalized. Of course, why would it? And then finally, you have UNC paths. This is for accessing SMB shares or WebDAV, and this is // server. So you've got weird paths if you allow UNC because you want to access a remote share and you're just checking for the double slash at the front. Well, you might have actually given someone access to the local file system, and you may not. You may try and look up the DNS name of question mark, and it'll probably tell you to get lost, but it should still work, theoretically. But of course it doesn't stop there, because why would it? And MS-DOS has an awful lot to answer for very many things in the world. And some of those is the behavior, the weird behavior of some of the Windows file system APIs. So there's a special casing in the file system APIs for opening certain devices. So in DOS times, if you wanted to, say, pipe a file to the COM port, you could specify COM1 as a file name, and it would open the COM port and allow you to write data to it. And even then, it might not have made that much sense, but that's how MS-DOS did its operations, and so that's how it works. And rather than baking this into just to say the command line, the command prompt in Windows, the Win32 API actually baked it into the create file call itself. So it's not special cased in the only place where you're likely to ever need it. It's special cased for any application you care to mention. And this has an interesting implication because you can't create a file. If you pass just COM1 to create file, it will open the COM port. It won't allow you to create a file called COM1 in the current directory. Silly. But you think, okay, clearly it would make sense if that only if you pass COM1 explicitly will it open COM1. What if I stick a full path in front of it? Surely everything will be fine. And of course, as you'd probably expect, it isn't fine. It still opens the parallel port, even though you've got a full path stuck in front of it. Great. Curiously, if you put in the device path, so you put // in front of it, it will actually open a file called LPT1. But now you've got a file you can't delete, or at least a normal user can't delete. It sits there, it taunts you, but you can't actually touch it. So for good measure, there's more edge cases. So for example, trailing spaces are removed off a file path. So if you pass trailing spaces, it removes them, and then you just get back path. And then in obviously a clear sort of consistency issue, // does not anymore, doesn't allow you to get those extra spaces in there. It removes them as well. Who knows why? But if you do the // it works fine. And now you've, again, created a file you can't delete. You can see this path. There'll be a file called path. If you go to rename it, it'll show you the free spaces, and you go, OK, delete. I can't find that file, because it opens path. It doesn't open path with free spaces. Canonicalization is also a funny one, especially when you get some of these other device path syntaxes. So, for example, you get what you expect if you do that. If you put // in, the canonicalization also seems to do what you expect. But notice how in the fourth line, you can actually .. away the drive letter, which seems a bit crazy, because that doesn't work if you just pass an absolute path. So if you crazily put // in front of a path when you're opening it, it can have completely different behavior than if you access it directly. And just to add things to the mix, the final device path syntax does no canonicalization at all. If you tell it to open .. something, it will try and open a file called .. And there's more fun you could have. Because this is actually what this really does, is it escapes into the NT object namespace. You can have fun. There's symbolic links in the object namespace. You can route things around. You can bounce it around from global root. And obviously, you can also do crazy things like converting what looks on the surface to be a local path. So you've got // C:, and remove that and then redirect it to a server, an SMB server. Awesome. Final thing on this, invalid character checks. There's usually a temptation, especially in Windows, I found, that if the NTFS file system does not support a certain file character, it's probably OK to ignore it when you're, say, building a command line or something like that. So all the obvious candidates there, there's double quote, // etc. But of course, never be tempted to prevent things like this, because there are ways around it. Canonicalization is the easiest one. You can just put in a double quote and then get rid of it by .. slashing. Of course, if someone canonicalizes it correctly, alternative data streams, which are, you'll see if, you'll probably see quite a few times, where you put semicolon, or you put colon and then an extra name, does not honor the NTFS file system character set. So even though the file name can't contain a double quote, the actual stream can contain a double quote, and that can also cause you problems. We've obviously got a performance aspect, and we got to try and mediate that. So we can do things like we don't send all your read writes through the system. But of course, if we do like a hybrid mode where we're passing the real handle back to the Sandbox process, we've got potential risks associated with that. And one is reparse points, which are NTFS symbolic links for directories. And obviously on Linux, say, you would have a syscall for symlink. But in Windows, all you need is a file handle to a directory. But of course, we're opening everything through the broker, and we can make sure we can't open a directory. You need to pass a flag and said, open a directory for me, and it will do so. So how do we get around that? Well, it turns out the alternate data streams comes in handy again. If you put in the dir name, : index allocation, it will open the directory, just because. No good reason why. Yeah, who knows, but I'm sure it made sense to someone. So I think the final sort of rundown of this is also, from a file system API, you've got very mixed semantics. Sometimes things will take file paths, which don't necessarily do the same thing as if you pass it to create file. So a good one is obviously the LPT1 stuff. Sometimes it'll do different things. But this is actually a bug I found in the install broker for ActiveX controls in IE. And this is obviously a very restricted version of it. But what it was doing, it was checking whether a DLL was signed with a certain certificate, and then if it was calling load library, and load library loads DLLs. It would be probably bad if you could just load arbitrary DLLs. So obviously, it can't do that. Now, ignore the race condition here. There's an implicit race condition here, but we'll ignore that. So we look at load library, look at how it processes file paths, and right at the bottom it says, if you don't specify a path, so a full path, it will do some clever tricks with the extension. If you don't specify an extension, it will slap .dll on. If you put just a dot, it will remove a dot, and you'll have a bare file name. So we can test this out. Clearly, the path should work. You shouldn't actually do this operation. But of course, if we actually test it, it does exactly what it said it wasn't going to do. And so you can get a timer check, timer use issue, and bypass the signature check. You get it to sign one file, and then it will load a different file. OK. Now, this was a bug I found in Chrome, which was due to, I think it's documented in one sentence somewhere. And you might, I think it's another sentence in the Windows internals book, if you're so inclined to look. And it was related to how you share large amounts of data. I want to share, say, some data with another process, ideally from the broker to the Sandbox process. And perhaps it's some configuration settings. It says, it has, say, a is the Sandbox enabled flag. So we make sure that only the broker can write to it and use access control to make sure the renderer or the Sandbox process cannot open it for write access. It turns out certain Windows resources, certain kernel resources opt out of security if they have no name. A section can have a name in the device path. If it has no name, because you're just sharing these handlers around, you don't care about the name, it has no security. That can obviously lead to problems. So I actually put a blog post up on the Project Zero blog about this, but basically, if I can remember what it's called, I can't remember what my own tools are called now. There we go. So common objects, and I've got a tool for this, but basically it will dump all objects for different processes which are shared between the two. So 3152. 3152 and 3256. 3256. Okay. And so these are all the objects which have the underlying object is the same between the two. And then you can look at these, and obviously some have names, but some don't. And so you might be able to then use that to abuse Sandbox. Oops. Wrong version of Chrome. And finally, come on, wait up, wake up. Okay, so there's various other things. I think I'm unfortunately running out of time. IPC is an interesting problem. Using name pipes, using RPC is an interesting challenge. And one of the bugs I found in Chrome was basically you open pipes using the //dot/ syntax, which can be canonicalized. And so obviously you can put // and open an arbitrary pipe, which you shouldn't have been able to access because. And is it getting better? Well, you can reduce the attack surface now. Windows 8 allows you to block Win32k system calls. So that gets rid of 1,000 system calls. And there's also the low-box token, which is used by enhanced protected mode in IE. And this finally gives you a way of controlling socket access without requiring your own firewall rules, which is cool. And it also blocks pretty much all reads. But unfortunately, they've done some weird thing. They've actually broken the IL check. So before the IL check was correctly handled, it took it from the token. So in this case, the token's running at low. But for some reason, the access check hard codes it to medium. So the IL check effectively has disappeared for pretty much any resource. That doesn't seem like it's probably a bug, because it's probably intentional, but I can't say, unfortunately. And finally, hopefully in the future, Microsoft Research came up with something called Drawbridge, which is a sort of process isolation sandboxing technology they're going to use in Azure and things like that. And hopefully this will actually become available. And maybe finally you can actually create isolated processes in Windows which is actually secure and hopefully you can't do stupid things in. Thanks for staying. If anyone's got any questions, you might have to accost me on the way out, but thanks for listening.